Good afternoon, everybody, and thank you so much for joining us in the second in the series of webinars on climate adaptation. And today we're talking about climate impacts and hazards. And I just want to point out a few things about the webinar platform. Most of you are probably getting very good at this by now, but we have all participants in listen-only mode, and you can interact with the handouts that we have, as well as ask questions. We will post helpful links in the chat box if useful. We will take your questions, so use the question box, and there's a little gray box that you can drop down and type your questions, and we'll manage all of those for you. And this webinar is being recorded, and all of them are being posted at the Mayors Caucus website, right on our homepage there. We will have a quick survey that'll follow up, just a routine how we're doing. And then just another note to help you prepare, if you have an opportunity to open the website for our interactive questions and dialogue, we use the Mentimeter platform, and there is a link in the slides, but it's menti.com, and you might want to open that on another device. So welcome. Turning it over to Mayor Kevin Burns.
Thank you, Edith, and good afternoon, everyone. Happy Friday to you all. And as Edith indicated, welcome to our second webinar series. I have the honor of serving as the mayor of Geneva, Illinois. I am beginning my 20th year shortly. I also have the pleasure of serving as the chairman of the Metropolitan Mayors Caucus Environment and Energy Committee. This webinar today will help inform our climate action plan for the Chicago Metropolitan region. We are one of only 4 regions in the United States chosen by International Urban Cooperation, a program of the EU to demonstrate regional collaboration on climate in the United States. The Chicago Metropolitan Agency on Planning and the Mayors Caucus are leading the plan development. The Global Covenant of Mayors for Climate and Energy provides the protocols and mentoring for global cities and regions. And all of you are here, I believe, and all the panelists believe, to help us, to provide your input now on the part of the plan about adaptation to climate change. All of us can share stories about the recent issues we've all faced with respect to heavy rains here in Northern Illinois. And I'm certain that topic is top of mind to all of you. So as we continue through the program today, we welcome your participation. We appreciate you being here. It's now my pleasure to introduce to you our first speakers. Dr. Ned Gardner is Engagement Manager for the United States Climate Resilience Toolkit, a clearinghouse for federal adaptation resources. Ned is a spatial analyst, ecosystem scientist, data visualizer, and science communicator dedicated to helping people understand and apply global change information for better decision making. By aiding and documenting the process of adaptation, he is at the forefront of defining how our nation adapts to a changing climate system. And joining Dr. Gardner is Mr. Jim Fox, a senior resilience analyst for NEMAC and Fernleaf, a public-private partnership between an applied research center at the University of North Carolina, Asheville, which he has led for 15 years, and a private company specializing in community resilience. He has worked with Dr. Gardner to create the Climate Resilience Toolkit and Steps to Resilience, and has worked with many municipalities and regions to build their climate resilience plans. Ladies and gentlemen, our first 2 panelists, I welcome them and I turn the table over to them for their presentation.
Thank you very much for that introduction, Mayor Burns. We really appreciate it. Ned, go on to the next slide. For those of you that were with us last week, this will be a little bit of a review for those of us that are just joining us for the first time. Hopefully this will get you caught up with the rest of the participants. We talked at the first of last week about the definition of resilience. And resilience is really being defined by the ability to really bounce back. And if you remember from the curves that we're looking at, that we tend to view our community as having a certain level of quality of life. And when a hazard occurs, it knocks us off of that line. And we have really then two choices that are facing us. Do we want to be more resilient, or do we want to be less resilient? And as we then move ahead, you can see that to be more resilient, we want to be investing now to be getting us onto a little bit higher baseline. So when a hazard does occur, we don't fall so far off that line below what's called a tipping point. Go on to the next slide, Ned. Ned and I live in the state of North Carolina, and a couple of years ago, our state was hit by Hurricane Florence. And that hurricane had a $17 billion impact on our state. And the reason I bring this up is we're going to be looking at impacts a lot today. It's really the way that we experience pain as a community. And the important thing about this slide is when we looked at that resilience curve, we're really not looking at a single curve. We're looking at multiple ones, because you can see then when we separate out that $17 billion impact, that's felt, individually on businesses, on homes, on agriculture, on other properties. And go ahead to the next slide. That we see then that when we are looking at what's going on nationwide, and in Chicago, you're experiencing the exact same thing we are in North Carolina, that we've got a couple different things going on. We've got continued growth, continued, number of people that are actually going to be experiencing the pain of these growing number of billion-dollar disasters. And the curve that's in the middle is a curve from NOAA about, the increasing number of billion-dollar disasters. But there's one other thing that's sitting through here, and that's really this idea of riskier investment. And groups like Moody's and Standard & Poor's are seeing this happening to communities nationwide. And they're the ones that give us the risk rating for borrowing money. And they're saying, unless you start building resilience, you're gonna have to start paying more for the money that you're borrowing for that. And so this is becoming a dollar and cents, as well as impact on personal lives. And the reason I bring that up is for Hurricane Florence, we only had about half of the $17 billion impact covered. That left us, just like it would leave you, as the locality having to handle that shortfall. So let's go to the next slide. Well, this is then what we're really talking about is we want to be looking at moving from that problem, that shortfall, to the solution. And that's why everything that we're doing here is having the assessment leading to the types of actions that we can be taking. So as you go on to the next slide, that really what we want you to be thinking about is moving from data to these decisions to inform adaptation strategies. Now you're going to be hearing a lot about data today from our great panel of experts. And Ned, go ahead and advance. And what you're going to be hearing is a lot about these climate stressors, right? The idea of temperature, variability, and change, this extreme precipitation and drought. But what we want you to be thinking about is this little mental model over here on the left, that these arrows in this mental model are showing a cause and effect, that as a climate stressor is occurring, it is having an impact on a hazard. And it's the hazard really then that is causing the pain to us, right? Mayor Burns talked about the flooding you've recently experienced, water shortages due to drought, extreme heat. But also just as important, it is the set of assets, people, infrastructure, programs that are being impacted by those hazards. Well, go to the next slide. We also know that it's just not climate stressors, but that growth in the development, the amount of impervious surface, more people, more demand for energy and water are occurring. And as we go to the next slide, we know then that there is change going on, that we talk about climate change, but there's also non-climate change as well too. This increased number of people, the increased demand for services. And so that as we look at all of those, we start to develop this mental model. And this is that mental model we want you to keep in mind as we keep hearing these presentations through the rest of today. As we go to the next slide, we talked about this last week, right? That these climate trajectories, this change of climate, and we started looking at the different ones, this increased average temperature, the increase of, different seasonal things, precipitation changes, whether too much or too little. And so it really then sets up this next slide, which is talking about then the same mental model. You can see this going down the middle, this climate to hazard to population or asset. That what you're going to be hearing from our next three speakers is really going to be talking about this left side, that this climate and its change is describing this frequency and severity of the hazards. And frequency and severity really then defines risk. Well, if you look at the other part of this slide, that then talks about the impacts, right? And the impacts involve both a hazard and an asset. So that as you're experiencing some of the flooding over the past week, that flooding was impacting things you care about, whether it's your own home, whether it's a business, or maybe a key road that gets you between the two of those. So go ahead and advance on, Ned, that what we really want you to be thinking about then is moving from where we were last week. And you remember in the Mentimeter exercise, we talked about primary hazards and we ranked those. And we started talking about, how important those are to us. But the next slide then shows the things that those hazards impact, right? These are the things we value, people we love, homes that we live in, businesses, community services like emergency responders or roads. And so as I hand the mic over to Ned and go ahead and advance to the next slide, we're going to go back into Menti just like we did last week. And I want you to be then thinking about this relationship of hazards to assets. So I'll pass it to you now, Ned.
Hi, everybody. So we'll give you some time to fill in the impacts that you're concerned with a little more insight now that you have about the relationship between hazards and assets. I'm going to continue the conversation moving through some more slides, reminding you that all of this that we're talking about in your adaptation plan fits into a framework that we call the Steps to Resilience. It's a framework that can help you keep your thoughts organized as you gather information, even iteratively or asynchronously. Jim and I are talking a lot about impacts so that we can understand hazards, and you're going to be hearing about impacts and risk today as well. Keep in mind that we move back and forth so that we can understand our priorities as a community. And for today, for right now, I'll focus a little bit more on flooding to keep our focus on where you've said you're most concerned. And to repeat Jared's points from last week, when we think about flooding, there are climate factors in play. Certainly the seasonality and the natural variability that we expect in rainfall is one factor, a major factor in understanding flooding today. And that actually interacts with some of the non-climate factors, such as the topography itself, the drainage characteristics of your soil, but perhaps one of the most important factors is Lake Michigan, because in a year like this year, when Lake Michigan is very high, the potential for flooding along the shoreline here is substantially greater. Of course, the development, Jim mentioned several times, impervious surfaces, drainage systems in our manufactured landscape, and the presence of developed land, in fact, increases not only the severity and frequency of flooding, but also the potential impact financially to our livelihoods and so forth. So we can begin to actually map out and understand the location and severity of different assets, such as damage to homes, basement backups, the sewer system itself, combined storm overflow systems, storm drains and the way they function. And all of these are related, of course, in the system where street flooding can be the result of and also contributing to the damage to all of these other assets. I've got some footage here from WGN9 from last week's flooding. This is taken off of YouTube. We're going to zoom in here on an area where some homes were submerged. You can also see a road that was submerged. And with an area as big as the Chicago region, there's quite a diversity of land uses. Here's an abandoned farm. You can see a lot of loose material, hazardous substances in the floodplain in this farm. Well, I said abandoned, but I actually don't know. But notably, there's gasoline or diesel fuel leaking into the waterway. Now that kind of hazard is very different than a parking lot that gets flooded, which might cause some inconvenience, or infrastructure for controlling water and its flow during floods. So understanding these different assets and their different risk profiles is very important. I was particularly gratified to highlight Channel 9 because Tom Skilling was someone that I worked with about 10 years ago on a climate communications project, and he really opened my eyes to heat and Chicago's terrible experience in the 1995 event. Naturally, in the region, people are very concerned about heat, and we're going to be talking more about that after my remarks. But I wanted to point out you have an opportunity to explore for yourself some of the ways that climate models that you'll be hearing more about from the rest of the panel can be used to evaluate and look into some of the potentialities that the future may hold. So we've built a tool called the Climate Explorer that provides downscaled climate projection information, which you're seeing here in shaded regions in red and blue for two different representative concentration pathways, which is 50-cent words for different levels of heating from greenhouse gas emissions to different pathways that our future could progress down. On the left here in gray is an envelope of what models say the past should behave like based on the physics put into the model, and these bars represent what was actually observed. So you can see a 30-year average with the line going through, and then positive and negative dips off of that average based on year-to-year variability. I'm going to invite you to use Climate Explorer right now. You can launch it by going to the Climate Resilience Toolkit, toolkit.climate.gov. There's also a handout in your control panel for GoToMeeting that you can use to follow these instructions. This handout is a PDF, and it takes you through the process I'm going to outline for you. You go to the toolkit website, you go down to the Climate Explorer, launch the tool, you'll exit the website, and then you can put in a location of interest. So let's pick on Mayor Burns. We'll go to Geneva, Illinois, and then you can go to the climate charts section. There are many different sub-tools within this tool. The climate charts brings up the graphs that I was just showing you, and then there are quite a few variables you can look at. This is average maximum temperature for a year. I'm gonna draw down to the days within a year with a maximum temperature greater than 95 degrees Fahrenheit. And notice this graph is gonna change. Now we're looking at the historical period where the number of days per year on average was about 1. And then we're looking at a trajectory of change over time with these two different sets of scenarios. I'm going to invite you at this point to go through that exercise yourself, and I'll give you a couple minutes to, in fact, do this. I'm looking at the clock, and I am realizing that I'm going to have to let you do this on your own, and I'm going to ask you to do that and multitask. I know it's a thing we don't like to encourage in our culture too much, but the reality is we all do it. So go ahead and follow the instructions in that handout, and I'll invite you to go again to menti.com, and I'm going to change the slide to a poll where you're going to tell me what, how many days more of 95-degree temperature you might anticipate in the year 2050, given the higher emissions scenario in the red envelope. So I'm going to leave this poll open while we transition to our next. Oh, I have one more point to make, and I'll make it quickly. I showed you the chart, but I can also show you a map of these data. Okay, so zooming in on Illinois, we can look here at the historical average temperature, which is showing these yellow colors, numbers of days down here below 5. Remember, we said it was around 1. And on the right hand, we're looking out at the end of the 21st century under the high emission scenario, and you can see in the Chicago region that that the number of days looks like all summer long. And so you can also explore this map for yourself. Pretty powerful. With that, I'll point out that we do have map information that depicts the heat islands in the city, and that's going to help us to understand the locations of vulnerable people and the things that we can do, including understanding the social and economic drivers of vulnerability, the things that we can do to address that vulnerability, the pain points by planting trees and providing access to parks. And that's really what this first step in the steps to resilience is about, is understanding exposure, having a team of people who are responsible or have resources to address a specific set of concerns. And I thank you very much for your time. I want to point out that the panel that's going to follow is going to shift focus now from a bit into understanding the climate system, as Jim alluded earlier. Thank you very much for your time, and I'll hand back to Kevin to introduce our next speaker.
Thank you, Dr. Gardner, and thank you, Mr. Fox. As we transition, folks, it's important to note that we are fortunate to have leading climate experts right in our own backyard. Our friends at Argonne National Lab and the University of Illinois often work with our Environment Committee and have been helping us with the Regional Climate Plan. We very much appreciate their support and their continued friendship. Dr. Wubbles and Dr. Sharma are also with the Illinois Center for Urban Resilience and Environmental Sustainability, otherwise known as CURES, and we enjoy their partnership very much. It's now my honor to introduce you to our next speaker, Dr. Rao Kodamarthi. Dr. Kodamarthi is the Chief Scientist, Department Head for the Argonne National Laboratory's Atmospheric Science and Climate Research Group. He is a Senior Fellow at the Computational Institute and holds a position at the Energy Policy Research Institute, otherwise known as EPIC, both at the University of Chicago. He has a PhD in Chemical and Biochemical Engineering from the University of Iowa and holds a certificate in Strategic Laboratory Leadership from the Booth School of Business, University of Chicago. Dr. Kodamarthi has nearly 30 years of experience in regional and global scale modeling of air quality and atmospheric composition, data assimilation, radiative transfer, and climate. So, ladies and gentlemen, please welcome our friend, Dr. Kodamarthi.
Thank you, Mayor Burns. I'm a local talent, as was pointed out. Unfortunately, my camera doesn't work because I work for the government. They blocked my camera. So, do I change the slides or somebody changes the slides?
You can change the slides yourself, I think.
Okay, good. So I'm going to talk about downscaling here. What is downscaling? Why do we need downscaling? And what are the common ways of downscaling are the three big questions I'll try to answer. By downscaling, I'm actually here referring to the climate model output downscaling. So it is a specific kind of downscaling that is applied to climate science, that is applied in climate science. Of course, you can do downscaling for various other things, but here we are talking about climate model output in particular. So why do we need a downscale climate data set? So many of you are kind of considering the resiliency questions and the adaptation questions and hazards, the big question comes up with what kind of data do I need and what scale do I need them? For example, if you are somebody working trying to figure out infrastructure scale, an infrastructure scale would be something like an aqueduct or a dam that you are trying to see what the risk to that is. So that is an infrastructure scale data. That's fairly specific. That is very small scale, but that's what you need, right? You need the data at that scale to answer the questions you have. The second thing could be an installation scale. Let's say you have a large water treatment facility in your neighborhood. So if you want to protect that or make it resilient to climate change, then you're looking at an installation scale data sets. Like Argonne is an installation. We are fairly large, but we are still an installation. So if you want to make Argonne resilient to climate change, you want data at that scale. And the third scale that we are talking mostly about today probably is the urban scale. At this scale, you're trying to protect the entire urban region. It could be as big as Chicago or smaller metro regions that most of the places around Chicago are. You're trying to protect them at the scale of your town. Then you need data that actually kind of affects the entire operation of the town. Like as you're looking at a system scale kind of thing. But does it affect my entire water? How does it affect my police and fire department and things like that? So you're looking at the city scale issues and how to protect them. Then finally, there is an operational scale that is of interest. So at this scale, let us look at the utility scale, like the electric department, the electricity that you get. They are mostly multi-state agencies. They are operating over multiple states. So you need data at the scale. So it's a kind of a more regional than the other three things I showed here. But these are a range of spatial scales that you need data for. And you're always looking for, if I want to make an assessment or evaluate risk, you definitely need data at that scale. What can climate models do in terms of spatial scales? I mean, that's your need. You need data at the scales, but what can a climate modeler do to get data to that scale? We do modeling at a global scale, which is most of the climate model operate at a global scale, and their resolution is what we call a resolution is about 100 kilometers by 100 kilometers. You can imagine this to be a kind of a pixel size of a global of the globe. So you cannot get finer than 100 kilometer resolution when you go into global scale. But the next scale to that is what we know as regional scale, where I do most of my work. And the regional scale is about 10 kilometer by 10 kilometers. So it's about a factor of a order of magnitude refinement in each of these scales as you go down. And the lowest scale is about 1 kilometer by 1 kilometer. There you're just looking at Chicago, for example. So once you go down each of these scales, as the resolution goes up by an order of magnitude, the computational power increases as the cube of the resolution increase. So if I go from 100 kilometers to 10 kilometers, the computational power I need goes up by about 10 cube. And the best computer we have right now are what are known as petaflops. Argonne is going to get an exascale machine by the end of this year that is about 1,000 times more faster than the computer we have right now. But to run a model globally at regional scale of 10 by 10, I will need a computer about 10 times faster than that. So it will happen in the next 5 to 10 years. But at this point, what we do is we approach this problem by doing downscaling, as I explained later. We will get to a resolution of 1 kilometer by 1 kilometer generate enough data sets to be useful maybe in the next 10, 15 years. So that's a resolution as far as modeling goes. So what is downscaling? Downscaling is a process of rescaling coarse resolution, let's say in both space and time. You, like I showed before, that's a spatial coarse resolution that you are trying to refine. And it's also, you can also do it in terms of time to a desired spatial and time scales for use in climate assessment and adaptation needs. So like I showed in the first slide, you want data set at a utility scale or an urban scale. You want data to be downscale, rescale the coarse data set to that spatial scale. So what does this actually mean? I mean, when you're downscaling the data set, you are trying to correct for the model bias, which by bias, we use the word bias quite a bit in climate science, which basically means that the difference between a model and observation when you look at historical data. So we call that bias. It is not the error in the, it's not that model is being biased to something, but just shows the error in the model. So we try to correct them when you scale the model, and also we try to add new information in the data set that is not available from the GCM output. For example, if you think about Chicago, you would like to resolve some of the issues with the lake, right? So that is actually adding information from on the lake into the model. The way we gain new information is by going to higher resolution. We actually run the model with a higher resolution physics. So we try to resolve more of the physical processes in the model as we go to higher resolutions. We also try to correct the bias in the model using historical observation and carry that forward. So when you do downscaling, you're doing two things. You're getting the model resolution to the resolution you want, and also you're adding more additional information that actually corrects the model issues as you come to the resolution you need. So those are the two things you want to do. There are two basic approaches for getting the data to the scale you want. One is called a dynamic downscaling method. The second one is called a statistical downscaling method. A dynamic downscaling method is essentially running a full global climate model physics on a smaller domain. Because I cannot run a 10 by 10 kilometer resolution model for the entire globe, what I do is I run it over just the North American continent or the lower 48, for example. That is so, but it does all the calculations as is done by a global model, sometimes more, but it takes the global model at the boundaries to come to the dynamic downscale. So we add more information by both increasing the resolution of the physics model, but also adding more of the details of the physics into the model when we do dynamic downscaling. When you do the statistical downscaling, what we do is we take historical observations, see how different they are from the model, climate model projections, and correct for them, and then take it forward into the future. So that is called a statistical downscaling approach. And it's, I will quickly tell you the differences between those two in a minute. So the dynamic downscaling quickly is shown here. What the dynamic downscaling I do at Argonne is covers the entire North American continent. There are several programs that do just for the lower 48, but you can pick a domain and do the calculation for that domain. What do we do with dynamic downscaling is why we want to do dynamic downscaling is shown in the figure on the left. What it shows is the top one shows a 50-kilometer resolution terrain, and the bottom one shows a 12-kilometer resolution domain for the California. What you can see is that the coast of the California is much better refined in the lower figure, which is at 12-kilometer compared to the 50-kilometer. And the Sierra Nevadas, the highest peak in the Sierra Nevadas, because you flatten out in the pixel, it's only about 2,400 meters in the 50-kilometer, but it increases to about 2,800 meters in the lower figure where I have a higher resolution. This is very important because the Sierra Nevadas, for example, the higher you are, the longer the snow stays in the snowpack, and also you get more snow. So both of them are really important for California to get the snowpack right. So you have to go to higher resolution to get that model doing right. So the other picture shown here is the supercomputer we have at Argonne called Mira, which has just been retired. And by the end of the year, we should be getting another one called Aurora, which is an exascale machine. An empirical statistical downscaling models, it's a mouthful, but it's basically we call them statistical downscaling models, are fairly simple in concept. The idea here is that when you have run a GCM or a global climate model, it has some differences with observations, right? If I have a weather station in my town, maybe I can compare that with a global climate model that is predicting for a 100-kilometer domain around my town, right? And then what you can do is you can look at the differences between the climate model and the observations and use that information to actually take it into the future and see how the projection should be changed to match more closely with your observations. So this has the advantage that you are correcting for the model bias when you're making a projections into the future. And these can be as simple as shown here in the figure on the right, where you see the observational figure for the current, and you adjust the mean of the whole entire graph to the right by seeing, let's say, the temperature in your town, as in your region, as determined by the GCM, increases by 2 degrees. You can move the entire curve 2 degrees to the right. So that gives you a climate in the future, and it's a very simple way of doing it. You can also change the shape of the curve based on how the climate model is actually projecting for the future. So this is known as delta method. It's very commonly used for a lot of things. But these calculations are really easy to make. You don't need a supercomputer. You can do it on your desktops. So it has been widely used. This method, a more sophisticated method based on this, is called LOCA, and it is used for the National Climate Assessment, as Don Wobbles will show you later in the talk. We can generate projections of scales of observation, including both grids and individual weather stations. So that's the advantage of doing this. And because of its simplicity, it has found a lot of applications and use in the user community. Just that it is probably the most widely used data set by anybody who actually is trying to use climate data, the statistical downscaling. So what are the differences between a dynamic and a statistical downscaling methods? A dynamic downscaling method, as I said, it's just a full physics-based model. So it produces a lot of variables, like how much, what is the relative humidity of the atmosphere, what is the temperature, what is the pressure, what is the wind velocities. Actually, you can see the changes in wind velocities from now compared to the future. These are important for example, if you are planning a huge wind farm in somewhere and which may see a decrease in wind velocities in the future. So it is important for this kind of applications like that. In precipitation, not only you get an average precipitation, you can get every hour or every 2 hours, every 3 hours, how the precipitation changes. So you can track better the extremes in the precipitation and temperature. It also gives you soil moisture and various other variables that helps you give estimate drought, for example, whether how frequent is the drought and how is it going to change in the future. As many of you know, regions around here are experiencing what is known as a flash drought, which is like you get this intense rainfall and you have the 10-15 days of where there's no rainfall. So there is irrigation even in northern Illinois right now, mainly because to deal with this flash drought conditions. These flash droughts have been increasing in frequency over the last 10 years, and it's an interesting local phenomena, regional phenomena that is not seen elsewhere in the world, but we are experiencing that in combination with the increasing intensity of precipitation, and we need to watch out for that as we go into the future. This may require additional bias correction once in a while because you want to correct for the model for the bias you see with the local observations, and you can correct it to make it more closer to what you want. But a lot of times you're looking at the differences and the percentages rather than the actual numbers in these kinds of projections. So it should not be such a big deal. It can be used. You don't really need observations to do this dynamic downscaling because it uses larger physics models and boundary conditions that are obtained from global models. We don't need to assume stationarity at a scale of resolved processes. This is very important, or kind of interesting problem in the sense that climate is not stationary as at the current time. As you can see in the future projections, things are changing. So stationarity means that the statistics of the observed climate kind of stay the same as you go into the future as they are now. So kind of the mean and the deviations are kind of, the variability is not changing as in going into the future, but maybe they scale differently. But actually that's not the truth. The shape of the variability may be changing. So this is the issue of stationarity, and dynamic downscaling does not assume that it is the climate is stationary. It can be a non-stationary, which all the GCMs predict to be. Statistical downscaling is often limited to a number of chosen variables. For example, temperature and precipitation. You can do for other variables like 3-4 variables, additional variables if you need. This is very computationally affordable, and this is the major advantage of this method. And also some people, for bias correction example, because this method depends on correcting your bias before you take it to the future, it makes you feel comfortable that, okay, I corrected for the model error, and then now I'm seeing how many degrees change is going to be in the future. So I have more confidence in this method because I have included observations in it, and it is influenced by observation. So it also gives you that comfort level that actually this has been corrected for model errors, model biases, and whatever projecting in the future is actually takes care of that. But other issue is that it is limited by available observations. If you don't have observations in your town or place you are in, it is a little harder to do the downscaling. You have to find something close by to actually key your downscaling, because you need about 20 to 30 years of observations to do this method properly. So if you have a weather station close by which has a long history, actually it makes it a powerful method. It also assumes that the GCM observational relationship holds in the future. Basically, you're assuming that the stationarity is, the climate is stationary and the relationship hold in the future. So these are all the variables I said we are downscaling. But when you're looking at risk and adaptation issues, the thing that that you're interested in is that, so all the downscaling that I talked to you before gives you hazards. I mean, it's trying to figure out what the hazards are. So climate models are best suited for developing a data set that keys into the hazards. But if you're looking at risk, there are two other factors. That is vulnerability of the area and exposure. So these have to come from other places, other tools. For example, this is calculations we did for AT&T recently for Savannah, Georgia. And what we are seeing here is a very high resolution 200-meter flood risk. It shows the amount of water level that could increase in this region as of in the next 50 years, for example. And it's overlaid on top of it is the resources that AT&T has in terms of cells and fiber lines. The black lines are the fiber, the green are cell. And it shows a method for mapping the risk of flooding onto this domain to that, so that you can plan. The problem with doing this is that this is actually, you have to run a couple of different models to get to that. It has a coastal flooding model, which runs a storm surge model, which runs at a resolution of 90 meters, and the inland flooding model, which is running at 200 meters. So you have to take the climate model, like a dynamic downscaling data is best suited for doing something like that, and then go down 2 more steps to actually get to that. You can go further and do for like a neighborhood scale. This shows a 100-year water depth potential for the RCP 8.5 scenario, which is a high scenario. Shows that in Nashville area, what are the areas that are most susceptible to more than 3 feet of water. So I will stop here. You can, these are the kinds of things that these data sets are useful. And I think this is one of the applications that probably very useful for doing risk and trying to understand risk in general. Thanks.
Thank you, Dr. Sharma.
Yep.
Ladies and gentlemen, it's now my pleasure to introduce to you our next speaker, Dr. Don Wubbles. Don Wubbles is the Harry E. Preble Professor of Atmospheric Science of Illinois and the Presidential Fellow at the University of Illinois. Dr. Wubbles served in the Executive Office of President Barack Obama, where he was the White House expert on climate science. He co-led Volume 1 of the 4th United States National Climate Assessment. He led a 2019 assessment of climate change impacts on the Great Lakes region. And Dr. Wubbles is the lead author of the 2008 Chicago Climate Action Plan. Ladies and gentlemen, please welcome Dr. Don Wubbles.
Hi, everybody. So I assume my slides will be coming up soon. And when they do, so what I'm going to do today is go over the kind of changes we've been seeing in the Chicago region and what the changes are likely to be over this century. I'm going to primarily do this by looking at LOCA. You've been hearing about that from Rao. Statistical downscaled results. These are analyses that we originally did for the 4th National Climate Assessment, and then are now adopting, we adopted them to the Great Lakes Assessment, and right now we're adopting them to a special assessment we're doing for the state of Illinois, covering the state of Illinois. We're doing this with the Nature Conservancy. Like all of these assessments, though, this is a pro bono activity, and I'm not getting paid anything to do these. We're just contributing our time to try to help, in this case, the Nature Conservancy take a special look at Illinois. So let's move on. So I think I have control. And so every year there are about 12,000 journal papers. These are the peer-reviewed papers in scientific journals that look at the questions related to what's happening to the Earth's climate, how the climate is changing, why it's changing, etc. And so there's a lot of papers every year. And for that reason, policymakers over time had said, well, we need to understand what all this means to us. And so they developed the concept of having assessments where scientists come together over some time period and try to evaluate how is the science overall changed? You know, essentially they integrate all the understanding from those 12,000 papers every year into these assessments. So the international assessments, which are called the Intergovernmental Panel on Climate Change, it's a UN body that brings the scientists together, puts out volumes of assessments about every 5-6 years. The last one that was published was during the 2013-2014 period. I led chapter 1 of the first volume, which was on the physical science changes. That's the picture on the left. And then there'll be another, the next set, it will come out beginning next year, 2021. And so that assessment was the 5th of those international assessments. The new one will be the 6th. Likewise, the United States decided in 1990 we should have regular assessments of how climate change is impacting the United States. And as Mayor Burns said, I led volume 1 for this last assessment. That's the middle picture here as the cover, and that shows an atmospheric river coming into California and ending the drought in the 2016 time period, at least temporarily. And then, but there were 2 volumes, and the second volume, which came out in 2018, looks at the impacts of climate change across many different parts of the country and across various sectors, transportation and energy and agriculture and health, et cetera, water supply, and all kinds of different issues are looked at in that assessment. What I'm going to do today is kind of an update on all of that. What do these assessments tell us? Well, this is the bottom line all in one slide. Our climate is changing. It's happening right now. It's not sometime in the future. We're seeing major changes happening now. And it's also happening extremely rapidly. In fact, about 10 times more rapidly than nature tends to change the Earth's climate. So, you know, we all know that over time, climate has changed extensively, going back millions of years. But climate usually changes very slowly. And so we're seeing extremely rapid changes compared to the experience that humans have had on this planet. It's not all about temperature change. It's not all global warming, as the media likes to talk about it. It's to me the most important factors are that we're seeing major changes in severe weather, particularly some aspects of severe weather becoming more intense. I'll talk about that more in a minute. And the other major change is sea levels are rising, and that is leading to lots of concerns about coastal issues, as well as other things that are happening in the oceans are also affecting the oceans in major ways. This is all happening largely because of human activities and associated pollution, particularly our burning of fossil fuels and land use change have increased the amount of carbon dioxide and some other gases in the atmosphere. Those are largely driving this change. The data is very clear about that conclusion. The other thing is we can slow this down. We can have a huge impact over the coming decades in terms of how much the climate will change, but we do know the climate will continue to change over the coming decades, over this century at least, because of things we've already put in motion. The emissions we already made will continue to have an effect over this decade, and we'll continue to make more emissions because we haven't totally stopped this issue. And so we're going to see more changes. Now, when we look at projections of the future, scientists tend to choose a range of different scenarios for how those emissions of these what are called greenhouse gases and also particles in the atmosphere can change. And so we look at a wide range of such analysis, going from a high case where we more or less stay on the continuing to use fossil fuels heavily. That's not as high as it could be. But there's many ways one can get to that pathway. It also doesn't just depend on fossil fuel use. All the way to a very low case where we try to keep the total change in climate below 2 degrees centigrade, which is what the United Nations had concluded in 1992 would be a dangerous level of change. We're likely going to be very much above that. In this analysis, I'm going to show you 2 scenarios. The high case and what I'm going to call the lower case, which is the blue one here, RCP 4.5, which will probably put us at about 3 to 4 degree change in Fahrenheit increase by the end of the century, whereas the high case is more like 8 to 10. So the kind of things we're looking at in terms of extreme events is, in particular, we're already observing these, and these trends are likely to continue, that things like heat waves are generally increasing in number of intensity. Cold waves generally are decreasing. It doesn't mean we don't get cold waves, we certainly do. We had one back in January, for example. But they're not as bad as they have been at times in the past. More precipitation is tending to come as larger events. That's in essentially all locations around the planet, even those places that are drying out. When they do get precipitations, it's more likely to come as a larger event than it has in the past. And that's particularly true here in the Midwest and also in the Northeast of the United States, where we're seeing particularly significant increases, and especially, as I'll show you, particularly in springtime in our region, where we're seeing very significant increase in precipitation, and that precipitation coming as larger events. This also means an increasing risk of floods, particularly in the Northeast and the Midwest. At the same time, some parts of the country are seeing an increasing tendency for more droughts, particularly in the Southwest and to some degree the Southeast. But as I'll talk a little bit later, even in the Midwest and the summers, we can expect a little bit of a mini drought kind of situation, more than we've had in the past. Some parts of the country seeing large incidents of wildfires. Hurricanes are becoming more intense. Tornadoes a little more difficult. Extreme storms are likely to be stronger, but tornado activity is more variable because of other factors in the science. But we do see an increase in outbreaks, more likelihood of a number of tornadoes if you get one. So the most recent assessment, as was mentioned earlier, is the assessment of the Great Lakes region. However, I'm also leading this special assessment along with Jim Angel, former state climatologist for Illinois, where we were looking at Illinois and surrounding states in a special assessment for the Nature Conservancy, and that should be published later this year. I'm going to show you some results from that assessment based on our new local analysis that we just did for that assessment. So it's probably, I think it's the first time these will have been seen. But first, a little bit talking about temperature in the Great Lakes region. We're seeing significant changes in temperature already in this region and in the Great Lakes themselves. Since 1901, the temperature in the overall region has increased about 1.8 degrees Fahrenheit. That may not sound like much, but when you consider the last ice age was about 11, 12 degrees cooler than now, we're actually talking about a fairly significant change in temperature. And most of that change has happened in the last 3 decades, 1.4 degrees relative to the 1901 to 1960 time period. So we're seeing a significant change in temperature and an acceleration of that change that is affecting us. If we look at northern Illinois, which is where I don't have it concentrated down to Chicago, but Chicago area, the Chicago region and northern Illinois in general look pretty similar. The changes in average temperature gone from roughly about a 50-degree average temperature, annual temperature, now, which is slightly, several degrees higher than it was back in the 1900 time period. But by mid-century, we're talking about something that's another 4 to 4.5 degrees Fahrenheit warmer overall. And by the end of the century, 6 to 10 degree warmer. And that's on average. I mean, the full range. The ranges here encompass all the different climate models, the 30-some climate models that were used to drive LOCA to look at this. So and in a sense, what that does is it really looks at the range of understanding of climate. But typically, the models are kind of in the middle of that range. So it gives you a pretty good idea of kind of expectations and what that range could be. And we're looking at a high case and a lower case, the high, and you see by mid-century, those scenarios begin to really change relative to each other. Before then, they're kind of based on the emissions we have now and largely affecting things. By mid-century, 30 years from now, we start seeing a significant difference between the scenarios, and that is really true by the end of the century. And on the right, you can see the region and how that would be generally affected by those two different scenarios for both mid-century and end of the century. Looking at the hottest maximum temperature, typically that's been on the order of 97, 98 degrees in northern Illinois region. By 2050, we're talking about it being more like 100 to 103 degrees. And by the end of the century, more like 104 to 108 degrees. So vastly different climate really than we have now by the end of the century. Even by mid-century, we're seeing significant changes. The hottest 5 days, which is the bottom graph, likewise, so this is averaged over 5 days, with 5-day periods. And so it's really looking at the question of a heat wave. You're still getting well over 100 degrees by mid and the end of the century in many situations. Looking at the number of days maximum temperatures greater than 90 degrees, right now there's typically about 10 to 20 such days in the region, and this again for northern Illinois. By 2050, we're talking 30 to 50 such days, and 2100, 60 to 90 degree, such days. So by the end of the century, we're talking about most of the summer being greater than 90 degrees in northern Illinois. Looking at the days greater than 95 degrees, that's typically less than 5 days now, but 10 to 20 days by 2050, and almost up to 1 to 2 months by the end of the century. So much, much different climate. Now looking at the number of days above 100 degrees, which typically less than 1 day or less an average. Currently going to more like 5 to 8 days by mid-century and 15 to 35 days by the end of the century, and with a big dependence on which of those scenarios we follow. What choice are we going to make as humanity to what emissions ranges are we going to follow? The bottom shows what about the number of days with minimum temperature less than 32 degrees. So that's what are the degrees where there's number of days where there's freezing. So currently, historically, that's been about 132 days over the last 30 years. And by 2050, we're talking more like 115 to 120 days. And by the end of the century, 90 to 110. So a significant reduction in the number of days below freezing. Next graph looks at the question of length of the growing season, where typically it's been on the order of 160 days. That increases by 10 to 25 days, or 15 to 25 days by mid-century, 175 to 185 days total. And by the end of the century, up to 185 to 210 days on average. So it's not taking into account the full range, it's just looking at the averages of the two scenarios. So significant increase in the length of the growing season. That has good implications for agriculture, but the decrease in the number of freezing days also has other implications about insects and weeds and all those kind of things that we won't go into today. Looking at seasonal rainfall, we've seen an increase overall in the winter, it's a very slight increase at this point, about 10% total annual increase in precipitation in this region, and with most of that increase occurring in the spring. And we expect those trends to continue with a significant increase expected in spring, much less difference between the scenarios for precipitation than for temperature. Summer's tending to dry out. They've already dried out a little bit overall. So by talking July, August timeframes, we generally are seeing a drying now, and that's expected to continue also. And fall's pretty similar to now in terms of precipitation. Now, going back to looking at the Great Lakes region as a whole, and then we can talk a little bit about the Great Lakes themselves real quickly. Precipitation has generally increased by 10% in the Great Lakes region. That's projected to increase by another 10% over this century, with more of that coming as larger events. I haven't really shown you the changes for larger events. I didn't have that graph available, but basically when it does rain, it's coming as larger events. So as much as 19% more precipitation for 1 in 5 year event by the end of the century than now. And so I see I need to finish up quickly. Looking at the watershed affecting the Great Lakes, this increase in precipitation will likely increase flooding across the region, but you combine that with higher summer and fall air temperatures, it will increase evaporation during the growing season. Less ice on the lake will also increase evaporation. Coupling summer precipitation that is increasingly variable and likely lower summer river flows will likely be lower by the end of the century. Now the question is, what about lake levels? This year we're seeing record highs on Lake Michigan, and that's likely to continue over the coming months based on the best analysis right now. But as you all know, the lake levels have fluctuated greatly in the past and will likely to continue to do so, but large uncertainties remain about future lake levels. I have begun to wonder that with more precipitation in the spring coming as larger amounts and an overall increase in precipitation, whether there is the possibility that higher lake levels might become the standard. But we really need to do the right analyses to do that, and we really need to do dynamical downscaling to look at that, and it's one of the things that Raul and I have talked about in the past. So I will leave it there. I thank you. Do remember, though, that the atmosphere around our Earth is a very thin layer, and yet that controls the climate that we live in. Thank you.
Thank you, Dr. Wubbles. Thank you very much. Ladies and gentlemen, I noticed that we may have skipped over an audience question via our Mentimeter. I would ask kindly if Dr. Gardner might help us lead through that audience participation exercise now.
I absolutely would be happy to. And people, in fact, did find their way to the Mentimeter poll that we had posted. And we're going to be using the results that you provide to us in order to gauge our comments for next week. So please do continue to participate. We have a closing question for Dr. Wubbles' presentation, and we're very interested to know about preparedness that different communities around the region perceive that they already have in place. So we will use that next week, and because we have such an esteemed panel with so much to say, I would encourage us to move on, Mayor Burns, and I can pass the ball back to Dr. Sharma.
Excellent. Ladies and gentlemen, our next presenter is none other than Dr. Sharma. Ashish Sharma is Illinois Research Climatologist at the Illinois State Water Survey and adjunct professor in the Department of Atmospheric Science at the University of Illinois. Dr. Sharma has a Master of Science degree and a PhD in aerospace engineering from Arizona State University. And Dr. Sharma is an expert in urban hydrometeorology and land atmosphere interactions. Ladies and gentlemen, Dr. Sharma.
Thank you, Mayor Burns. Okay, here I go. So I'm going to take a little bit deeper dive on urban heat impacts and solutions in the Chicago region, and tell you guys, okay, what basically heat means and what basically urban systems mean, and maybe that might intrigue you in these questions. I'll start 200 years back. Let's go to Luke Howard. 200 years back, he was an amateur meteorologist with broad interest in meteorology. he was the first one to recognize the effects of urban areas and on heat on local climate. So that was the time of Industrial Revolution, and what he realized is the summertime temperature over London was a little bit warmer than the rural and natural surrounding temperature. So that was the first sign that time Howard found that urban areas are kind of hot and because of anthropogenic changes. And since then, it's been more than 200 years just trying to understand the heat impact within urban areas and still struggling to find solutions. Okay, so I'll be talking mostly about three things. First, try to explain what urban systems are as an atmospheric scientist for me, what do they mean to me? And after giving an overview of that, I'll talk about adaptive choices. What choices do we have if we have all these extreme heat impacts? And finally, how can we create some kind of a decision support tool so that we can help city planners and mayors and stakeholders to make those strategic decisions? Okay, so this is a schematic talking about the interface between natural and an urban environment. And let's look at what happens during the daytime. So during the day, when you have sunlight, we have over the agricultural area over the left side, you have cloud cover because of the sunlight. A lot of radiations passes through the cloud cover and some are reflected back. The radiations which passes through the cloud cover are trapped and leads to heating and are long-lived radiations typically, and they absorb radiations, and the maximum temperature over the rural and natural areas increases slowly. While over the urban area, again, because of the tall skyscrapers, radiations are trapped at times because of different kind of surfaces. There are high albedo and low albedos as well. There are different heterogeneities within the urban environments. You have a lot of different kinds of built infrastructure, houses, roads, transportation, vehicles. There are ponds, oases, leads to irrigation impact. Impervious areas like built structures leads to an impervious or drying impact. And emissions from pollutants from the vehicles also leads to heatings in some ways. And on top of the urban environment is the entrainment that happens because of the interaction between the low level wind flow and the upper level wind flow. And eventually the maximum temperature over urban areas is higher or same in comparison to rural areas. So there's not that much difference between the temperatures over urban and rural areas. While in the nighttime, still because of cloud cover and greenhouse gases, they still reduce the outgoing radiations, so the heat is still trapped, and the minimum temperature increases faster than the maximum temperature. Okay. Over the urban areas, the building starts radiating. You see entrainment happening, mixing of upper and lower levels air happening. And the minimum temperatures kind of increases faster in comparison to rural areas. So the concept of urban heat island is predominantly over the nighttime, where the nighttime temperatures are relatively warmer than the over urban areas than the rural areas. And also the diurnal temperature range, which is the range between the maximum and the minimum temperatures of a day, that is reduced over urban areas. So these are the basic conceptual framework that I'm talking about when we talk about what do we mean by urban heat island and other things. Okay, so with this framework, I'll go into how city of Chicago looks, Chicago Metropolitan area looks like. Before that, let's look at this animation, which shows an infrared movie over looking at downtown Chicago. And this gives an idea to common people that urban environments emit radiations and that leads to heating, which is quite evident, but we forget to think about it. And if you look at, there's a colleague, one of my colleagues walking past in front of the camera, and you can see that humans also contribute to urban heating. And this is kind of important because as IPCC predicts that around 68 to 70% of populations will be urban in next 30 years. We'll have around 20% increase in populations in urban areas. So we need to be vigilant and make sure that we are the part of the problem as well, part of the solutions living in urban areas. And if you look back at the history, mid-1990s, we had a heat wave. We recorded 106 Fahrenheit at Midway Airport, more than 400 plus deaths that happened back then. 10, 12 years earlier, Chicago came up with the Chicago Climate Action Plan, which one of our esteemed panelists, Don Wubels, led. And they came up with plan and strategies to implement urban heat adaptation initiatives in face of climate change. But that plan was just for city of Chicago. But right now we are having these webinar series so that we can find out, okay, what can we do as the bigger Chicago metropolitan area, so that these impacts are not local, they're integrated, they're regional, as well as we need to understand them in a bigger perspective. So if we look at this whole region as in this conceptual framework, which is surrounded by natural areas and Lake Michigan, we have a lot of different kinds of urban heterogeneities, and try to depict them here. We have industrial area, we have some kind of a vegetated form within the urban area, greenery, we have big tall buildings and small households. So there's a high energy stress, high urban heating, a lot of pollution, so the urban environments are a lot stressed. And if you look carefully, I have humans which are showing that higher crime rate as well. So there's a little bit unrest in the urban environment. So you can imagine, and you know that climate impacts are kind of disproportionate within the cities. So our goal is that we want resilient urban environments with adaptive choices. We want less energy stress. We want low urban heating. We want a lot of more green infrastructure, like green roofs, school roofs, a lot of trees, permeable pavements. And at the end, we want people, the residents living in, are happy and prosperous. So with that goal, what can we do to achieve those things? As an atmospheric scientist, here I overlay our really high resolution 1 kilometer model data over Chicago region. And this shows the daily profile over this region. And this looks very fascinating, but and this is much better resolution than what we see on weather channels, the heat maps and the precipitation maps. But if you talk to a local resident, I would say this looks good, but it doesn't provide the information that is needed at neighborhood and at household levels. So what can we do when we have such good capabilities and expertise? How can we massage everything together so that we can make impactful decisions for our urban communities? So my research is understanding what happens within this atmospheric layer, and also a bigger part of my research is how can we combine fundamental research that we do with translational research to serve the society. So there are a few concepts I'll be talking about. First is we need to bridge urban scales as scientists. We are talking about city scales, what happens at the city levels. Here by city levels, I mean, say, bigger Chicago metropolitan area, what happens at that scales. We need to understand what happens at local scales, around 2-3 kilometer scales. How are the flows? Where are the hotspots? Where are the pollution centers at those scales? At the same time, we need to understand what happens at micro scales, okay, within a small neighborhood of few houses, because that's where people live and it impacts them. At the end, we want to understand what happens to every individual, every resident living in this neighborhood. And then we want to connect that back at the city scales. So if you want to do this thing, we need tools which are useful for large, medium, and small cities that can benefit from them equally. We need simple tools for our planners, for our cities, for our communities, so that they can make those strategic decisions. At the same time, we need ways in which we can talk to the complicated tools and train simple models. So it's a feedback loop. So I'll give you a few examples. At regional scales, for example, when our atmospheric community, when we do research, we at times treat 1 kilometer resolution as a very high resolution. And assuming within a 1 kilometer resolution, as you all know, there's a lot of heterogeneity. So assuming 60% of area is urban, so a lot of climate models assume that when 60% is urban, the whole area is urban. When you assume that, you only account for the contribution on the left-hand side panel. But we need to account for contributions of non-urban areas within the urban grid. When we account for that, you can see the temperatures are lower. So that when we account for these contributions in totality, we can get a true depiction of how and what our urban heat structure within the area is. So these are the lessons that we need to be very careful about at regional scales. While at local scales, we need to invest in resources where we have micro-scale models. You might, as a resident, you might feel like when you take breaks during office hours or want to go for a walk, you find that particular side of the household or the street are really pleasant, where you want to enjoy. So this type of modeling efforts can show, okay, where are those hotspots at such neighborhood scales, at such local micro scales? And what can you do to so that the other areas which are relatively warm or are polluted, so that you can reduce those pollutions or make them cooler by these kind of modeling approach. So we need these integrated approaches. Now I'm going to wear a hat of a social scientist, which I'm not, but the importance of urban areas for us is not to understand just the atmospheric flows happening at different scales, but also how the city are by itself. If we look at last 40 years income data over just the city of Chicago, this is the research that we are currently doing. We can see the spread, the divide between the city increasing, and that's something I hope similar within the Chicago metropolitan areas. And we are trying to pursue this and looking at the larger scale. Chicago right now is 8th in income inequality among nation's largest cities, and that's huge. We don't want everyone to be rich or poor, because healthy level of inequality is needed to encourage growth and prosperity. So, and what's that inequality level? How much health inequality? How much inequality should be? So we need to work in those integrated fashions. And here I show the crime analysis. So these are the places where you see a lot of crimes happening in Chicago. So how can we use these tools combined with the atmospheric sciences expertise to make those strategic decisions? And I'll be talking about that shortly. Okay, so what solutions do we have? So with this framework, let's look at the solutions. So the potential solutions could be, and here are just a few examples. We can have cool roofs, and I'm thinking as an atmospheric scientist, so it doesn't mean there are not these are the only solutions, but these are one of the few solutions. You can have photovoltaic roofs that are solar panels. You can have permeable pavements. We can have electric cars, and we can have green roofs. So we basically need to diversify and not think about just one solution, but a mix of solutions, which are technological engineered ecological mix of solutions. Okay, and I'll talk about why we need a mix of solutions. So please remember this slide right now. Okay, so as a climate modeler, it's hard for us to just talk about one roof and imagine, okay, what will happen because of that roof over the bigger Chicago region, because the impact would be diluted. So we usually do a broad study, and we assume homogeneity, some level of homogeneity. And here we are looking at the differences if we convert all the Chicago metropolitan area to 100% green roof, and then look at the difference plots of, okay, how much is the reductions in temperature. And this is intuitive that if you have a lot of greenery, the reductions in temperatures would be high. But it gives a thought process. Okay, this is something useful. So that if you look here, the temperatures can reduce up to like 7 to 8 degrees with green roofs. And likewise, we did study over the cool roofs as well, where we saw the decrease in temperature up to 10 degrees centigrade. Oh, remember, these are in Celsius, not in Fahrenheit. So Fahrenheit would be even higher. But at the same time, if you look at the wind speeds decreased, and this was not expected, and we didn't think about that when we were doing the study. This is new, and I'll talk a little bit more about this too as well. So the lake breeze intensity decreased when we had the green roofs. Okay, so here are the vertical profiles. The reductions in temperatures not only led to the near surface temperature, but within the boundary layer as well, and it's likewise for the wind speed. Okay. So if you install green roofs, and here green roof are the proxy I'm using for adaptation strategies. So you can think about having water in a pan on a stove, and on a high flame, you can see a lot of convection happening. Okay, and when you reduce the flame, that is assumed that is analogous to having a lot of green infrastructure, the convection reduces. And this is what we see along this cross section. When you use green roofs, the convection reduces by, say, half a kilometer, from 2.5 to 2 kilometers in height. At the same time, the convection rolls that are happening, those trends have decreased. So you can imagine the pollutants which are next to the surface, they won't be lifted up, and because of the reduced lake breeze, they won't be advected. So if you aggressively use one strategy, then they might have negative consequences. We did some chemistry-based simulations, and we saw that the results were true. Our hypothesis was true. This is ozone. The ozone was well mixed and up till like 2 kilometers, but with green infrastructure, the boundary layer height decreased, and we saw higher ozone levels over Chicago metro region. But this doesn't mean that green roofs are not a good solution. The message is we need patching of green roofs, because that can help us have these convective cells be spread out so that we can have a lot of mixing, and that can reduce, that can benefit from air quality as well as we know it, we are going to benefit with respect to reductions in temperatures. So we wrote this paper, and it was well received, and it got some coverage where they said green and cool roofs provide relief for hot cities, but should be cited carefully. So that's the message. We need diversification. We can't just think about one strategy. So if we have a lot of mix of strategies, then it's helpful. Okay. So finally, where should the cities invest? I'll breeze through this topic in the interest of time. We have heat waves, and heat waves are the silent killers. So people don't realize, many people don't realize that heat waves lead to higher mortality. So we try to create a decision-making tool, and we are trying to understand how can we help communities. So here I'm going to give 3 examples: roof temperatures, AC consumptions, and heat vulnerability index. And if you look at all 3 in totality, and if I give it to Mayor Kevin Burns, who is looking at this right now, and say, okay, these are the 3 maps, where would you like to invest? He's like, okay, this is all over the place, but how can I decide with limited amount of money? So we try to create a simple strategy where we say, okay, let's treat green roofs as a proxy. These are the reductions in temperatures with green roofs. Put it on a scatter map, give it a 50 percentile cutoff based on heat vulnerability. You have reduced the sample size, and then put air conditioning consumption, give it a 50% cutoff. Now you have reduced your sample size a lot. And these are the strategic locations that you can invest. And this gives the benefit that we can now have reductions in temperature at the same time, avoid the unintended consequences of poor air quality because we are not doing over the whole area. This is useful, and this was also well received. So I'll end my talk with this last slide, building upon Jim and Nat's talk, that right now our environment is facing multiple shocks. We are not having one shock, but we are having multiple shocks. And that tests the robustness. Okay, a city might be a lot more robust or less robust in dealing with the shocks. And if we have these multiple shocks, we test our resiliency. Cities' infrastructure might collapse. It might have a slow recovery, or it might have a fast recovery. So we need to understand what are the trigger points. And these trigger points need not necessarily be infrastructure based. It can be based on other things as well. So we need a lot of interdisciplinary approaches so that we can try to figure those out. I'll leave this slide for you to think. Basically, we need fundamental applied translational and collaborative research so that we can understand more. Over to you, Mayor Burns.
Thank you very much, Dr. Sharma. Appreciate it. I believe we're going to have a couple questions, or at least field some questions. I'm going to ask my friends Edith Macra and Cheryl Scott from the Metropolitan.
And before we get to that, Mayor Burns, we do have one final Mentimeter poll that we're going to activate right now.
Okay.
Thank you for responding to your the polls earlier. We're having a fairly low response rate, so I'd encourage people to go ahead and jump back into Mentimeter. But this question gets to prioritization. So we're sort of looking ahead to how would we spend $100 if we had it today, a figurative $100, maybe 100,000, 100 million, what have you. And this question is designed to ask you to allocate those dollars to regional versus local projects, as well as research. And we'd be interested to see people's opinions about allocation of resources. And with that, I think we can, while these numbers are coming in, turn the mic over to Edith, as you suggest, Mayor Burns, and
thank you.
Ms. Macra can lead us through a bit of Q&A.
Fantastic.
Great, happy to. So as one would expect with the presentations we've had, we do have a question about the availability of data and some questions about the scale. So this would be for any of our panelists, if we could answer what data are available today and where do we get them?
So I will, Don, you want to answer that?
Go ahead and start. I'll add.
So there are lots of resources. Statistical downscaling, as I said before, which is very high resolution, can be up to a kilometer scale. You can get from various sources. The easy thing is there is ClimateNet. I cannot name all of them right now, but there are tens of sources for that. For dynamic downscaling, it's a little bit more tricky. They are generally developed by PIs, scientists. So I have one. Me and Don have developed one. We are working on another one. There are other people, like NCAR has one data set, which is National Center for Atmospheric Research. So there are some international efforts going on. So that is a little bit more limited, but statistical downscaling, you can get a lot of them.
So just to add to that, the statistical downscale analyses are based off of the previous global model results. There really is a need right now to update those analyses based on the latest global model results that are being done for the new IPCC assessment. But the local results, like I showed, those are readily available. We can provide those to you. And in fact, the data that's within the climate toolkit that Ned and Jim talked about earlier is based off of that same local data. The one thing to be aware of, though, is that data is limited to temperature, precipitation, and humidity. And so for other variables, you have to go to the dynamical downscale. And I would say that the analyses that Rao and I and my group have done, Rao's group and my group have done, are I think currently probably the best available. The 12-kilometer resolution, there just isn't another data set quite comparable to be using for looking at local regional impacts.
And I'm showing the Climate Explorer on screen right now because this is a representation of the LOCA data that came up in the talks earlier. So people can actually download data here. When they go into the charts, they can select a data set that they're interested in and in fact download a comma delimited file that could go right into Microsoft Excel. And you have the instructions for how to do all that in the PDF that we provided as a handout in the first part of the webinar.
But please do feel welcome to ask us if you want to know how to use those data sets. Rao and I are part of a new book actually that looks at the entire question about how one uses downscale data sets.
And I appreciate the sort of the reference to the region and how some of this data has been used and the planet has been used for Chicago. And as we are embarking on our regional climate plan, do you have any advice for us about using this data, or if you have thoughts about other regions where the data has been successfully utilized in planning?
There are a number of different studies going on using these data sets, these type of data sets. I don't think there's no one community I would say, oh, they're way out ahead of everybody. I think everybody is still way behind in looking at climate resilience overall. But I do suggest that if you want to use the data sets, that interacting with us would be a useful idea, because I think that as scientists we provide an input to how to use those data sets that could be very helpful to you.
And I do have a question about appliances that contain freon and freon substitutes that are often stolen as turned in for scrap. This is actually a recommendation from the Drawdown publication. Does anybody have an answer?
What's the question? I'm an expert on PFCs, so.
Has there been any thought given to providing return of appliances that contain freon and freon substitutes that are often stolen and turned in for scrap with the lines cut? The freon is a serious contributor to climate change, according to Drawdown.
Right. Okay. Now I see. Yeah. They. I think the Refrigeration Society is still accepting the extraction of the chlorofluorocarbons so that those don't end up in the atmosphere. I'd have to do some checking to find out who you have to contact to do that. And it was being done through NIST, the National Institute for Science and Technology, and for standards. I'm sorry, standards and technology, and something like that. And I'd have to check to see exactly how you go about doing that. But yes, it is good to extract the freons, which are chlorofluorocarbons, from those refrigeration type units.
Ned, do we have any? Do you want to share any results or more questions on Menti, or are we?
Sure, we can definitely review where we were. So remember, we asked several questions. Let's go back to the beginning, and we'll see what people said. We did ask about different impacts that people are concerned about, a lot with flooding. We're hearing that consistently. And so there's some more detail here with regard to flooding. I can highlight one here. Investments in infrastructure are at risk. I'm concerned that we make investments in heavy infrastructure. So this gets at the planning stage and capital investments and making sure that climate information is incorporated. So for example, water utilities incorporate up-to-date downscaled data into hydrologic models that are then used for assessing wastewater, stormwater, water treatments, and so forth. I know that bridges and the transportation system are also possibly needing some design updates based on changes in the design storm requirements. We asked people to tell us about the number of days of 95-degree temperature expected by mid-century, an increase in the number of days by mid-century. And it seems like we have several people saying about 3 and several people saying about 7. I found when I did the analysis for Geneva, Illinois, my answer was around 7. And I'm sorry. So no, we have, I'm reading these numbers are the number of responses at different levels. The average response was 13.1 days. So I think the person who, people might be reporting absolute values out here on the right. And the question was about the difference in the number of days. And I suspect that the mean here is close to 7 days increase by mid-century, which is very soon. And as Dr. Wobbles pointed out, you know, the exponential nature of these curves is that the different scenarios don't diverge till mid-century, and really the acceleration itself continues to increase. So that's a very quick response in climate change to be seeing just 30 years.
This is Don. I got 5 to 15 days in my analysis, so it's right in there.
Very close. Yeah. So
Very good.
when you analyze, we should clarify then, Don, that analysis was for the state, and we're showing people county level.
That was for Northern Illinois.
Yeah. So the county level data are going to be pretty darn close to that. We asked people about the scale that they're interested in, and I'm very interested to see that when it comes to extreme heat, a lot of people are very interested in the region as a whole. Thinking about regional heat waves. We only had about 7 people respond to this survey. For hot spots during a heat wave, we have a bimodal distribution with a few people saying sort of the, not at the neighborhood scale, but maybe a municipal scale, and some people thinking really locally. And for extreme precip, we seem to have people interested very local, maybe municipal scale and regional. So that reflects some diversity in perhaps the roles and responsibilities that people play in developing the action plan, the climate action plan. We want to be sure that we are supporting, documenting, and supporting the kinds of actions that can be taken at different scales, because responsibility and resources are available and can be allocated at different scales. And so the way that we develop strategies in the subsequent steps after today's webinar will differ when we look at those different scales. Same with flooding. It seems like we have almost a flat distribution, even distribution from local to regional. Really interesting responses there. For preparedness, mostly people are are leaning towards sensing that they're unprepared, although it does seem like some steps are being taken, at least perception is that some steps are being taken to prepare for flooding. I would expect that is true, given that this is a phenomenon and an impact that you're experiencing already. And so all in all, what I'm seeing here is a desire for support around focusing on flooding. Finally, we have this prioritization question, and we have a fairly even representation of priorities with a gradation from focusing on regional flood management or reducing urban heat islands at a regional level. Second priority being incorporating climate adaptation into development priorities. So this, you know, since CMAP is a major partner in this plan, we do see an opportunity to align with the principles that they've laid out in the ONTO 2050 report. As land is redeveloped, there's an opportunity to incorporate climate smart and climate aware policies. And so there's some interest there I can see. And again, regional shows up in the third of 5 priorities with policy and priority setting. People do want to support research, especially research that supports decision making. So the office I work for funds a lot of research on decision support per se, and perhaps we can talk a bit more about that in the future. And finally, green roofs in my community. People are interested in, to some degree, in some local solutions around that. And so Edith, that's what we got from the participation today, and it's a very interesting set of feedback that we can bring into our future discussions.
Well, we so much enjoy the Mentimeter and the opportunity to participate when we're all working remotely. Let you wrap it up, Mayor.
Nothing more to say, but thank you very, very much, especially to our panelists and to all of you who participated and attended today. We hope that you can join us again a week from today on June 5th for a discussion regarding climate risk and vulnerability. And then again on June 12th, which is also a Friday, to discuss adaptation planning and prioritization workshop. With that, I bid you all a very happy Friday. Please be safe this weekend as Illinois begins phase 3 of its Restore Illinois plan. And we hope that you'll participate again a week from now. So long, everyone.